back to another Night Sky News for June 2020. Like, seriously, how did it get to June already? I don't know how this happened, but we have so much astrophysics news to talk about. But first of all, let's start by thinking about what we can see in the night sky in the coming month. First up, on the 18th and 19th of June. So if you're watching this the day this video comes out on the 17th, I'm talking about tomorrow morning and Friday morning. I want you to look out for, you guessed it, my favorite, the Toenail moon as usual. Now, this is actually pairing up again with Venus, and unlike how in previous months of the year we've been seeing Venus in the evening sky, Venus has sort of moved round to the other side of the sun now, so we see it in the morning sky. It's still very close to the sun though, so it's going to be very, very low on the horizon. So this is going to probably be a little bit of a difficult one to spot. If you do catch it, obviously send those pictures my way. Then a little bit of a fun fact for you. On the 4th of July, Earth is going to be at its furthest position away from the sun. It's something we call aphelion as opposed to perihelion, where it's closest to the sun, which is in January. So at the minute, we're in the middle of Northern Hemisphere summer. Apparently, it's currently chucking it down outside here. Doesn't really look like summer to me.
It's raining sideways!
So this just shows you that, you know, our distance from the sun in our orbit has no bearing on our seasons. That's caused by the tilt of the Earth's axis. If you're curious, as I was, the Earth will be 94,500,000 miles away on 4th of July, as opposed to 91,400,000 miles away when it is in January. That's about a 3 million or so difference. And it means that the sun will actually be about 3.6% smaller in the sky than it usually is. Now you can actually see this in photographs that have been taken with the proper filters so that it's actually safe to photograph the sun. But you know, if you're watching a sunset at the minute and you can see it dipping below the horizon, you're not going to be able to really notice any difference in the sun's size with your naked eye. It's just a little fun fact to know. Then on the 5th of July, we're back into full moon territory. And as it rises in the southeast, it's actually going to be rising with Jupiter and Saturn. So it's a really easy way to be able to spot Jupiter and Saturn. Jupiter will be the brightest thing after the moon, and Saturn will be sort of a very yellowish looking star that's not twinkling because it's a planet that's nearby. If you need one of those apps to help you make sure that that's what you're seeing, then download one of those. So I'd recommend, if you have binoculars anywhere in your house, breaking them out and actually checking out what Jupiter and Saturn look like through binoculars. Jupiter is particularly spectacular because you can see its 4 main biggest moons as well, the Galilean moons, and if you go back night after night, you will see them change positions, which is always such a fun thing to do. Unfortunately, you can't see Saturn's rings with binoculars. You do need a telescope for that. If you do have a telescope though, what a great way of spending the evening and trying to find Saturn, because it's so close to the moon and Jupiter at the minute. It makes it quite easy breaking out the telescope and looking at Saturn's rings in all their glory. Then on July 11th and 12th, if you time it right just before sunrise, you'll be able to see Saturn and Jupiter just setting in the west, while Venus comes up in the east as the sort of close to the sunrise, and you'll have Mars sort of directly south as well. So really spectacular time right now in June to actually see the planets. So, you know, the moon sort of rising with Jupiter and Saturn is probably for the night owls, but this sort of perspective is really for sort of those people who like to get up early. So whichever one you prefer, you know, you can try and have a look for in July. Jupiter and Saturn are also going to be in what we call opposition soon, which is where they're sort of directly opposite in the sky from the sun. So the sun, Earth, and then say Jupiter make a nice line sort of in the solar system. And that's when those planets are actually brightest. So Jupiter will be July 14th and Saturn July 20th. That's when they will actually be the brightest. But really all through the month of July, they're going to look really, really nice and bright in the sky. So as spectacular as the planets are going to look this month in the night sky, let's move on to what's been going on in astrophysics and space exploration news, because there's so much to talk about. The big news this month was obviously the very successful first ever crewed mission of SpaceX's Dragon craft up to the International Space Station. It was the very first commercial craft to take astronauts up to the ISS and sort of really marked this sort of turning point in how NASA is going to manage, who takes care of what. They're going to have commercial companies launching astronauts into space, basically doing the relatively easy stuff, and they're going to focus on how, we get people back to the moon and then use that to get onwards to Mars. So astronauts Bob Behnken and Doug Hurley made it safely to the ISS. Their return is scheduled maybe sort of July, August time. NASA and SpaceX haven't quite decided when they'll come back yet. In the meantime, whilst they're on the ISS, there's some, spacewalks planned to change some batteries and power packs on the outside of the ISS. And they're also going to be there on site to help NASA and SpaceX analyze, the launch data and the orbital data and the performance of Dragon on its way to the ISS as well. And they're also going to be testing its capabilities as a lifeboat, that can be used in emergencies. So the idea is that they are going to fully shut down Dragon, which is how it would usually operate after returning astronauts to the ISS. And then they're going to reboot it back up again to check that reboot, happens smoothly, but also that it can be done very quickly in an emergency. So first up, I want to talk about this Nature paper that came out this month by Nicastro and collaborators. Now, a lot of you sent me the news report on this story this month, either on Twitter or Instagram, and it was great to see your excitement about it, but there was so many misleading headlines about this work because they made it sound like what they found was dark matter when in fact it was missing normal matter that they found. So back in the 90s, astronomers essentially did a big census of all the visible matter in the universe. They essentially would okay, how many galaxies can we see? How many stars are in those galaxies on average? And so how much normal luminous matter is there in the universe? And they sort of also then attributed for a lot of stuff that we can't see, like dust and gas as well, to try and sort of put a number on, how much stuff actually is there. And they found that it was about half of what cosmology, i.e. our best model of the universe going from sort of the Big Bang to now, predicted should have been there. And that sort of might sound troubling. You might be like, well, maybe the model's wrong, but that model does a pretty good job. Everywhere else there's still a fair few problems with it, which we talked about on this channel before, but of all our models we have, it does the best job. And so a lot of people sort of thought, well, perhaps where that matter is that we actually haven't been able to see is in the sort of what appears to be empty space, right? It's in the space between all of the galaxies, but no one had ever been able to prove that before until now, until this study. They actually found that this matter is residing in what we call the cosmic web. The sort of is that structure that binds all galaxies together with this web of gas and dark matter. And they've done this in a really cool way. What they've used is fast radio bursts. This sort of mystery of these radio signals coming from space that we maybe can't quite explain yet. Those who watched last month's NightSky News know that there was that exciting piece of evidence that maybe they're coming from magnetars, but we don't want to sort of jump the gun yet. But they've been able to use these fast radio bursts and the frequencies that they're receiving from the fast radio bursts. So, what frequency is the actual wave? Because different frequencies will be affected differently by matter that is in the way. And how much they're affected can then tell you how much matter it's encountered on the way here. Because fast radio bursts come from very distant galaxies and they're very, very bright, that signal, we can still read it. And so then what you can do is by knowing the distance from us to the galaxy that it's come from, we can then work out the density of the matter that is in that intervening space, the intergalactic space. And so what this paper has found that it's roughly about one baryon, i.e. one normal particle like a neutron or a proton, per cubic meter. So pretty empty, but still not completely empty. There is still matter there. And although a cubic meter, is pretty big on our scales to just have one particle in it, if you think about how much space there is between galaxies that are separated by, billions of light years, it adds up, and it can account for all of that missing matter from the 90s, where they were missing sort of half of it to match cosmological predictions now. Just for comparison's sake, to put this into perspective, the intergalactic space is what 1 baryon per cubic meter. It's the space between galaxies. The space between stars, the interstellar space in the Milky Way, we also consider that to be very empty, right? The space between the sun and the nearest star is empty. But actually the density of normal matter there is about 1 million times intergalactic space. It's 1 million baryons per cubic meter. So it really puts it into perspective, that space isn't really empty, but intergalactic space is probably the emptiest. So the reason there's a lot to talk about this month is because last week, the 1st to the 3rd of June, was the 236th meeting of the American Astronomical Society. Of course, that didn't happen in person at all. It was all virtual and online, but it means there was lots of results presented and discussed as well. But often when this happens, you don't have the written up paper, the written up work to go with it yet, because it's sort of announced as like, oh, here's this cool thing we think we found, like what do you all think about it? And there's a lot of discussion that takes place around it before like the paper then gets like fully submitted and everything. So the one I want to talk about next, this result, it really did catch my eye. It's something I'm very interested in, but the paper isn't out yet. So maybe take everything with a little pinch of salt because it's not been peer reviewed yet, but it's still a really cool result. So this talk that was given, and then, they put out a press release and everything as well, was on the magnetic field around the supermassive black hole in the center of the Milky Way, which by itself is a really cool result because it's a very poorly understood topic as well, sort of like magnetic fields around black holes. But the reason this caught my eye is because it was also from the SOFIA team. And SOFIA is a NASA telescope on an aeroplane. Now, this is not just for like shirts and giggles. This is to get the telescope above 99% of the Earth's atmosphere, because the telescope on board this aeroplane is an infrared telescope. And the Earth's atmosphere absorbs so much infrared light that really nothing makes it down to the surface. Now you might be thinking, isn't it just better to like launch a telescope into space rather than like having to fly an airplane every time you want to use this telescope? Well, yes, and we are planning to do that with the James Webb Space Telescope that's coming very soon, hopefully in 2021 if the schedule is stuck to this time. But in the meantime, let's put a telescope on a 747.
All right, why don't we see if we can bring this back to topic?
Now, you would think that sort of gravity would be the reigning force around a supermassive black hole because, well, they're just so massive. But actually, as material falls into the surrounding regions of a black hole, it gets pulled into what we call an accretion disk. The same way that the solar system is all in one plane, everything is sort of moving around the sun. And the gas that falls in, it gets superheated because it's traveling at such ridiculous speeds as it's spiraling around that black hole. There's so much energy there that energy actually ionizes the gas that's around the black hole. What that means is that it takes the electrons from in atoms and removes them. It gives them enough energy to escape the atoms. When that happens, you no longer got like a neutral gas. You've got like a gas with positively charged ions. That's something we call a plasma. And as that plasma sort of moves around, you've got moving charges. Moving charges set up magnetic fields. And then because they're moving, the magnetic fields get all sort of like interwoven. And it's very, very complex. It's very difficult to study, not least because, a magnetic field is invisible to us. We only ever see, the influence of, say, like a bar magnet when we can put it down, on a big collection of iron filings. And those iron filings all line up to show you the magnetic field around it. So what we really need to study this is sort of like the space equivalent of iron filings, right? And thankfully, we do kind of have that with interstellar dust. It's basically just lots of little particles of heavier elements, including, metals like iron. People know that I like to call this, supernova poop that's just littered, through space. And usually dust is really annoying to astronomers. Personally, for my work, it's so infuriating because what it does is it absorbs a lot of the UV light, the very high energy light, especially the sort of stuff that's coming from that plasma that's spiraling around the black hole, and it re-radiates it in the infrared. Now, the light that's re-emitted will be polarized, which means it likes to move through space in a very certain way. So light is a wave, you know, that moves sort of like this, and if it's coming towards you, it'll be moving like this. But that's a very specific direction that it's moving in. It could also be coming at you like this, or like this, or like that. So light bulbs give out light that can come at you with any sort of direction that it likes to move in, any polarization. And the same is true for the sun, for example, as well. And that's why your polarized sunglasses work, because they only let in the light that's traveling in a certain way, and so they filter out a lot of the sun's light. Now, this dust that's re-radiating in the infrared, the way that the light will then be orientated will depend on the magnetic field. So if you can measure how the light has arrived, whether it's like this, or whether it's like this, or this, then you can work out what the magnetic field is doing around the black hole, and essentially they'll act like your little iron filings. So then this is what they found. This is a composite image, which means it's two separate things going on here. So in the background, the sort of grey is actually a Hubble Space Telescope image of the center of the galaxy. But anything you can then see in sort of green and blue is the Sophia infrared data. It's basically like the raw light that the dust is emitting. And then you can also see those sort of like streamlines on there as well. They've been drawn to show sort of the direction and the polarization of this dust that traces out the magnetic field. Also, complete side note here, but the credit for this image is someone called L. Proudfit. And all I could think of when I saw that was... Anyway, Joan Schmaltz, on behalf of the Sophia team, announced this at the AAS last month. And not only did they release this image, but they also announced that the magnetic field strength and pressure was much higher than previously thought. As I said, it was thought that gravity would always dominate around a supermassive black hole. And that might be true really quite close in, but actually on the outskirts of that accretion disk, it looks like it's actually the magnetic field that's going to dominate, you know, how that material is going to move and where it's going to be funneled to. So that has huge implications for not only, you know, how supermassive black holes grow, but also how they interact with their galaxy and sort of the medium surrounding them as well, which if you watched last week's video about my PhD research, then you'll know that that's something I'm really interested in. So I am going to be keeping a very close eye out for this paper coming out, because I think it's going to have some really interesting conclusions to look at. Next up, I want to talk about this paper that came out this month by Bartodekar and Consolis, which was using the Hubble Space Telescope to try and find the very first stars that ever formed in the universe. Now, one very useful law of physics is the speed of light. The fact that light even has a speed limit and it's not instantaneous going from one place to another means that as we look at more and more distant galaxies, that light has taken a lot longer to reach us. So if we can look really far back, we can actually see galaxies where the light left those galaxies right when the universe was only, say, 500 million years old compared to the sort of 13.8 billion years old that we think it is now. Now, one thing astronomers are very interested in is when specifically the very first stars and galaxies formed. And you might think, well, you know, just look back as far as you can until you don't see anything else anymore. But the problem is that the universe is expanding, which means the light from distant galaxies gets stretched on its way to us. That's what we call redshift, and the further distant you look, the more redshift the light will be. It means that stars that gave out visible light, optical light, that, you know, we use to see the universe around us nearby, is stretched so much that it's no longer visible by our eyes anymore, by optical telescopes, for example. It's shifted so much that it's gone into the infrared part of the light spectrum, and sometimes even beyond that as well. The other thing though is that these galaxies are also very faint. So you need a really good telescope that's going to collect a lot of light to be able to even spot them in the first place. That telescope at the minute is the Hubble Space Telescope, but it can only detect light in a very narrow wavelength range. So just above sort of the blue end of visible light into the UV, and just into the infrared part of the spectrum, just below sort of red visible light as well. So it means that you get to a point where even the very brightest UV light given off by stars in very distant galaxies is redshifted so much that it's no longer even visible by Hubble at the very infrared end of its detection range. So as much as we'd like to be able to just look until we can't see any more galaxies anymore, the question is whether Hubble can even see that far back in the first place. So this paper by Barton Akar and Consolis this month was trying to put a limit on how far back Hubble could see to be able to say, okay, the first stars and galaxies must have formed before this at least. How they did this was so clever. So they took this image of a quite nearby galaxy cluster. It's called MACS J0416.1-2403. It's named after coordinates. What can I say? If you want to give it a better name, let me know in the comments what you think it should be called. Anyway, this cluster is relatively close to us. The light was emitted about 4 billion years or so ago. But what this cluster does is, because it's in the foreground from our perspective, in front of sort of the background galaxies in the very far distance that we actually want to study but are very faint, what this foreground cluster does is it acts as a lens, a gravitational lens. It curves space-time by Einstein's general relativity, and what it does is as the light from those background galaxies is coming towards us, it gets bent and magnified for us here on Earth. So it's as bright, the light that we know was emitted sort of like 13 billion years ago, as the light that was emitted 4 billion years ago that we can detect in this very nearby cluster. Which is great, but then of course you've got all of the light from this foreground cluster of galaxies getting in your way. And so what the first thing that the authors had to do was actually to, first of all, model for where all those galaxies were that were in the foreground, and then subtract that light off to be left with just those background galaxies that they wanted to study. And that's what you can see here in this image. What you can see here are the galaxies that Hubble could still detect, and the light from them left them when the universe was only about 500 million to about 1 billion years old. So this is very ancient light. Now, obviously, the big question is working out whether what you have detected is actually the very first galaxies and first stars, or whether it's just the limit of what Hubble can actually see that's not redshifted out of its range. So what Barton Akar and Consolis did was measure something called the UV slope, which is often referred to as the Greek letter beta. And essentially what it does is it tries to say how much blue light compared to how much red light a galaxy has. So if you were going to make a plot of how much light of each wavelength or color you're receiving from a galaxy, you would see it would have some slope upwards or downwards. If the slope was negative, it would mean it would have much more blue light, aka lower wavelengths, or if the slope was positive, then that would mean it would have much more red light, aka longer wavelengths. Now, according to our models of how stars evolve and then like what a big collection of stars would give you in terms of like the light that you would get at each wavelength, the most negative slope you can get, i.e. the bluest slope, is when you have very young hot stars that have formed out of pristine hydrogen, the kind that you would only find in the very early universe after the Big Bang. Because now we're sort of 13.8 billion years later, the stars that are forming out of that supernova poop again, right? After a star has lived and died, it's converted a lot of the hydrogen into helium, but then also into things like carbon and nitrogen and oxygen. So for example, the fact that our solar system even exists and is made from things like carbon and we breathe oxygen tells us that the sun formed from gas left over by a previous generation of stars that maybe also even formed from a previous generation that maybe could have been the very first stars in the universe. So what Barton Akar and Consolis did was measure this UV slope, this beta, for all their galaxies. Obviously, they weren't actually measuring it in the UV because it had actually got redshifted so much that it was actually down in Hubble's sort of like infrared regime when they actually measured it. But what they found was that none of them had slopes that were negative enough to be the very first generation of stars. So what this paper was able to do is put a limit on when the first stars in the universe were born. And because they didn't detect any evidence for them, and their most distant galaxy, the light from it, left the universe when the universe was only 500 million years old, it means the first stars have to have formed when the universe was younger than 500 million years old. Now, the first author of this paper, Roshana Bartodekar, is actually my old office mate from when I worked at the University of Nottingham. She was still a PhD student when I joined after just finishing my PhD. And I figured, you know what, it's been ages since me and Rach had a chat, so I gave her a call so that we could chat about this really cool result together. So this result is really cool, being able to put a limit on, how early the first stars formed, but it's kind of sad that Hubble can't see them, right? So what is the plan? What's the next step?
Yeah, it is sad, but it is also very exciting at the same time, because in our work with Hubble, we were able to look at a very young universe that is just 500 million years old. And the good thing is that we will be able to get an answer to this question, because JWST, the James Webb Space Telescope, it is scheduled for a launch next year in 2021. And JWST will be able to look even further back in time, as far back as when the universe was just 200 million years old. And so, yeah, it will help us answer this very fundamental question.
So I guess you're really hoping then to get time on the James Webb Space Telescope after it launches. Have you already put in an application, or are you still waiting?
No, so I'm a member of the GTO team, and so yeah, I'll have access to some of the very first proprietary data. So yeah, that's super cool.
Nice. That's a privilege. That's really cool.
That's a privilege, yes.
So I guess for you, the first stars in the universe is the equivalent to my sort of obsession with supermassive black holes then.
Yes, exactly. I'm very excited to know what were these very first luminous sources which caused this reionization. We don't know, and this is one of the most fundamental questions, and it is also one of the unanswered questions in astronomy. And so, yeah, it will be good to have an answer to that.
That was so cool to hear from Rach there. So thanks so much to her for taking the time to speak to me and also to you guys as well. I've linked her Twitter profile if you want to follow her down below in the video description, along with the paper that she's written up about this result and all the other papers that I've talked about in this video too. I remember when I did the video in January on the Radcliffe wave, that a giant wave of gas they discovered in the Milky Way, and I got on the scientists that were actually responsible for that result. I remember the comments were just overwhelmingly in favor of doing that again, because it's just so nice to hear from the people who are so enthused about their work and put sort of faces to the names that are actually behind these pieces of paper that we look at all the time. So I'm definitely going to try and do more of that in the future. So I hope you enjoyed that. If you did, subscribe, hit the like button, maybe check out my book that came out in the US and Canada last week as well. It's already out worldwide. There are links in the description below if you want to do that. But all that's left for me to say, I think, is thanks for watching, and until next time, happy stargazing. So astronauts Bob Behnken and Doug Hurley made it safely to stop flickering extra light. Why are you flickering? Stop it. Stop it. Stay. I'm gonna give everyone seizures. So astronauts Bob Behnken and Doug Hurley? Sorry, Doug. So astronauts Bob Behnken and Doug... I did it again. My God. Doug. His name is Doug, like the TV program. Oh Christ, does my hair keep catching my mic? Ugh. Just because it's so long. It's been 2 months till I can get a haircut as well. The question is whether Hubble is able to see that far back. That Arbok.